Okay, well, I had a moment here. I wanted to record just got a quick video for you. I wanted to talk about writing a first law equation. And I'm testing out equipment here, trying to see how well this works, so bear with me, but if this works good, I'll post this on YouTube. This is going to be helpful, I think. Writing a first law equation. Step 1. Draw your system. If you've taken a statics class, this is just like drawing your free body diagram. If you draw your free body diagram and it's drawn well and correctly, it is much easier to actually write your equations, your equilibrium equations. And if you've not had statics and that doesn't mean anything to you, that's okay. Draw your system, step 1. Step 2, draw energies crossing the boundary. And so identify all energies crossing the boundary of your system, and that's of course going to be heat, work, or mass. Those three, heat and work, are the ways energy can cross the boundary directly. If mass is crossing the boundary, the mass has its own thermal energy, we often call enthalpy. It also has its own kinetic energy. It could have its own potential energy, although it's pretty rare we deal with that in an intro thermodynamics course for engineers, but it's possible for mass to have a significant change in potential energy. But anyway, these are the three types of energy that can cross the boundary. Now, step 3, the left hand side of the first law equation is add the ends, subtract the outs. What that means, very simply, is the left-hand side of the first law equation, we're going to add all the energies coming in, and we're going to subtract any energies going out. That's, and we'll do just a kind of real simple bare bones example in just a second. For the right-hand side of the equation, is the energy change for the system. Now, if that's for us in our text, if that's a chapter 4 problem, that's most likely a stationary closed system. The right-hand side is just going to be delta U. For a chapter 5 problem, if it's a steady flow control volume, the change of the system will be 0. And we'll see those as we go along. This is a simple 4-step process. Now, if we apply this to just a simple closed stationary system, let's say I've got some kind of a piston cylinder. So we see a few of those in chapter 4. A nice classic closed system that we might deal with. So let's say I've got a piston cylinder, and if I'm adding heat to that piston cylinder, and it's got boundary work occurring, I'm just going to label that as boundary work out, assuming that it's expanding. So the first law, if those are the only types of energy crossing the boundary, the first law again says, well, I've drawn my system, I've drawn the energies crossing the boundary, I've got a heat and I've got a work. Left-hand side of this equation, because the first law again says that if you take the total rate at which energy comes in minus the total rate at which energy goes out, that's equal to the change in the energy of the system with respect to time. Now, if we simplify this for a closed system, the total energy going in is just going to be the heat in. The total energy going out, well, it's got boundary work occurring, and we're assuming that's in the out direction. Now, if I compute it and get a negative sign on that, and if the system's being compressed, this actually ends up being work in. That's okay. That's my left-hand side. That's it. I've got heat in, I've got work going out. That's the entire left-hand side. That's this N minus L. That's equal to the change. If it's that's equal to the change in the energy for the system. If it's a closed stationary system, then this is simply M delta U. And that's it. No reason to overcomplicate it. Draw your system. Draw the energies crossing the boundary. Left-hand side is add the ends, subtract the outs. Right-hand side is the change. Now again, we've mentioned before, some other thermotexts, this is what kind of the approach our thermotext takes. Some other thermotexts would have you use a slightly different sign convention where workout is always positive and heat in is negative, or heat in is positive, and that's not how we approach it in this with this particular text. This text, this is the process. That's how you write your equation. If this is if this is an exam 2 problem, this equation right here is probably going to be 10 to 15 points if it's correct, depending on how complex the problem is. So it's a very crucial, important step, and I wanted to just kind of record a separate standalone video just for this, and wanted to see how this software works here. So hopefully enjoy.